Chapter 5, The Skeletal System, Screencast 1. This chapter focuses on the skeletal system, and in all honesty, was probably one of my most favorite of all systems. Back in graduate school, we had a bone lab, and many of my friends that I went to grad school with are some of the premier bone physiologists in the country at this point in time. But one of the things I want us to remember here is we need to approach bone as a living tissue. And it's kind of hard because quite often we're used to seeing skeletons, things like that. But bone is dynamic. You're going to hear the term remodeling. The other term that I like to use is to describe bone as a plastic tissue. And what that means, bone will respond to external forces, and I'll use loading. So high impact activity is a good example of things that will increase bone density, whereas not being active, which is a big issue in the United States these days, is a negative example that will actually decrease bone density. So we'll talk about that along the way. Now, when we look at the skeletal system, it's mostly made up of connective tissue. And there's three types of connective tissue that we need to introduce here. Bone, and that's actually the hard component of the skeleton, and that's what we're probably most used to. Ligaments, we talked about dense fibrous connective tissue previously in chapter 4, and a ligament is defined as connective tissue that attaches bone to other bones. So we'll come back to that. Sprained ligaments are a very common injury. Cartilage, now that is a specialized connective tissue, and it's made up of collagenous fibers and elastic in a gel-like matrix or ground substance. And what cartilage does primarily, a good example, is to cushion vertebrae, and it actually reduces friction in joints, and that is hyaline cartilage or actually articular cartilage. Now, when we look at bone overall, it's a combination of non-living and living tissue. So that is really important for us to remember. The hard, rigid appearance is the non-living extracellular component, and it's made mostly of calcium and phosphorus. Now, the living tissue is made up of three different types of cells that we'll introduce a little bit later, and those cells play a primary role in the formation of bone and remodeling. Remember, I introduced the term plastic, indicating that bone is going to respond to external forces. Now, importantly, we need to look at what the overall functions are of bone. Support kind of makes sense, the rigid support of our body. Protection, so bones actually protect a number of really important vital organs. If we look at the rib cage, if we look at the skull, and also the vertebral column. Bones actually act as a lever system, so movement is really important. So muscle will attach to bones, and when muscles contract, that contractile force is transmitted to bone, and that's actually through tendons, another type of connective tissue that we'll talk about later. We previously addressed the role of the formation of blood cells and formed elements. We see that that actually takes place in red bone marrow. And probably what most people think of, first off, is the storage primarily of calcium and phosphate. So once again, we want to keep this in mind. Now, as indicated, bone has a hard inorganic matrix of calcium salts, and there are two different types of bone. We have compact bone versus spongy bone, and we'll kind of talk about that along the way. Now, the cells, and this is the living component that we find, are osteoblasts, osteocytes, and osteoclasts. We'll be coming back to that. Now, when we describe bone by shape, there's three general shapes that we use to describe the types of bone. We use long, flat, and irregular. Now, a couple of other terms that you want to get used to are osteons, and that is kind of the functional unit of bone. The next figure, we're going to take a deeper dive into some of this terminology, and the Haversian system, that's kind of canals. And periosteum, that's that connective, that outer connective tissue covering. A really good example of the periosteum would be, kind of imagine that you've got a rack of ribs. The meat is gone and you have that tissue that's attached to the bone itself. That is actually the periosteum. Now here, some general terminology that you need to be familiar with overall. So epiphysis, that's the actual ends of the bone. Diaphysis, this is the shaft, and here we're talking about a long bone in particular. Femur. And if we look at the periosteum, you can see that they've peeled it away here. Okay. Very well vascularized. That's important. Now, yellow bone marrow typically is found going to be within the compact bone within the shaft, and then within the spongy bone, and we'll talk about the differences there in just a second, that's where the red bone marrow is. Okay, so there's an awful lot on this diagram, but it's important we take the time to introduce this terminology. Now here, this is the osteon, and if you take a look, a very common description, here we can see a photograph of an osteon. Quite often, growth rings on a tree are used to describe what that osteon actually looks like. So it really does look really cool under a microscope. Here we see the blood vessels and nerves, and that's all basically this canal system. Okay, that's responsible for making sure bone is getting the nutrients that's necessary, and also the innervation. So anyone that's ever broken a bone before, you know it's well innervated because it's pretty painful. Okay, now osteocytes, these are the cells, and what they are doing is they sit in a shallow chamber or depression called the lacuna. Okay, so a shallow depression called the lacuna, and that's where the bone cells, and here we see an osteocyte overall. Okay, now here is that spongy bone, and look at the difference. Okay, so it has lots of struts that are called trabeculae, and this bone in particular is very well adapted to take stress from multiple directions because nothing is going in a single direction. When we look at long bones in particular, compact bone, it's especially good at handling compression forces. And we'll talk a little bit more about that also. But the anatomy of bone has a lot to do with how it actually functions. Now, ligaments, as noted before, is dense connective tissue. And ligaments connect bones to each other. So that's their role. A ligament is going to connect bone to bone. We talked about the type of connective tissue, so the fibers are very regular and densely close to each other. And when we look at what a ligament does, it actually adds stability to the joint. Okay, so where a bone meets bone is known as a joint, and quite often those bones are held together by ligaments. Okay, and that ligament is providing the overall stability that we see. Now, once you sprain a ligament or stretch it, it doesn't go back to its previous length. So that joint will not be as stable as it used to be prior to the injury. Now, cartilage, what it really does is provide support under pressure situations. And the types of cartilage that we want to actually introduce are fibrocartilage. And the best example of fibrocartilage are the intravertebral discs between our vertebrae. And we'll take a deeper look at those a little bit later. And then the meniscus in knee joints. Some of you may have torn a meniscus and had to have arthroscopic surgery to repair it. So that's a really good example of fibrocartilage. Now, when we look at hyaline cartilage, that is the embryonic structure that the skeleton actually develops from. So the term is ossification. Okay? There are a number of animals out there, fish in particular, that do not have true skeletons. Shark are a really good example. They actually have a cartilaginous skeleton. Now, hyaline cartilage is also known as articular cartilage, and it covers and protects the ends of our long bones in joints. And what that does, it protects us against friction. Now, osteoarthritis, that's actually a wearing away of that articular cartilage. Then we have elastic cartilage, And the examples there are the epiglottis, the outer ear, and it's very flexible. So we don't spend a lot of time talking about that. We're focusing primarily on fibrocartilage and hyaline cartilage. Now, when we look at the development of bone, it begins early on at the embryonic stage. And it starts off with a cartilaginous model. And this is during early fetal development. And this cartilage is actually formed by chondroblasts. So that blast is important. That actually is a cartilage-forming cell. Now, as the fetal development continues, osteoblasts, these are cells that are actually producing and laying down bone. They actually replace the cartilage with bone. Now, during childhood, what we're going to see are primary and secondary ossification sites, and this goes into how bone will actually become longer. And during adolescence, that elongation occurs at what's known as the growth plate, and we'll see that in just a second. Now, during pre-adolescence, growth hormone will play a role in stimulating the lengthening of bone. As adolescence comes on, estrogen and testosterone are going to be the primary stimulators for bone lengthening. Late adolescence, estrogen and testosterone, they actually cause the replacement of the cartilaginous growth plate with bone. Now here is an overall progression. There is an animation that's available in the main PowerPoint. There also is another animation that you can take a look at in the animations PowerPoint available in the Chapter 10 materials on Blackboard. Now here, first 2 months of fetal development, we really see it's all cartilage. And chondroblasts form this hyaline cartilage, and that's basically the rudimentary model of future bones. At 2 to 3 months, we now start to see the periosteum starting to develop, and also look the beginning of blood vessels starting to come in. And that's going to be moving osteoblasts into the area from the periosteum. During childhood, these osteoblasts are now secreting osteoid and enzymes, and what that does, that facilitates the deposition of hydroxyapatite crystals, and that really is the bony matrix. Okay, so it's a combination of calcium and phosphorus together that forms the overall bone. Now here, okay, this is the cartilaginous growth plate. And what happens during growth, basically the epiphyses grow further apart. That's how that bone actually lengthens. And so that growth plate and long bones, they move further apart, and the bone will begin to lengthen and widen during adolescence. Now here we can actually look at the growth plate, and what's happening, the chondroblasts are depositing new cartilage at the outer surface, and the osteoblasts play a role in converting cartilage and bone at the inner surface. So this growth plate is really important, and a child to actually have a fracture at the growth plate while they're growing can be a significant problem.